I did Fourier just in the discrete case, the linear algebra picture of Fourier. So I'll do kind of the Fourier series, the integral, continuous.
Hello, everybody. Before we continue with the ring model, do you find the lecture notes useful? So, as you may have seen, we are a bit behind. We haven't published the working memory lectures yet, notes yet, and we are already talking about the ring model. Will it be useful for you to receive drafts as we go?
Yes.
Okay. So we will make an effort to send you the working memory is more or less written except for the biological background. So we can make an effort to send you drafts as we go along. And again, any comments, even this sentence is unclear, you have a typo there, comments will be useful. Idea would be to send you revised notes according to your comments towards the end of the year. Okay, so the topic of today's class is the ring model, and I'd like to remind you what we are trying to model. So in many cortical regions, we see, if we look at the firing rate of a neuron as a function of some external feature, one-dimensional feature, this we're thinking about the orientation in the visual cortex or direction in the motor cortex. So this would be 0, and this would be 2 pi. We see some kind of selectivity. Maybe I shouldn't write here. I cannot delete it. But I guess you get the point. And this would be an example of one neuron. And we'll see other neurons, for example, whose selectivity will look very similar but shifted. And if we consider all the population of neurons, population is rather homogeneous, each neuron having its own preferred direction, preferred orientation. And the question that we ask is, how does this selectivity emerge? What's the role of recurrent connections in the cortex in this selectivity? And to address this question, we postulated a particular model or particular pattern of connectivity, which is known as the ring model, in which neurons reside, not physically, but conceptually or functionally reside on a ring, each neuron having its own preferred orientation, direction, and with connectivity, which depends on the functional distance between the neurons, and input that also depends on the functional identity of the neuron along this ring. So more formally, we were considering the connectivity matrix that Jij is equal to 1 over n J0 plus J1 cosine of theta I minus theta j, and external input to neuron I which is equal to h0, 0 plus h10 cosine of theta I minus some theta, which would be, let's call this, I don't remember the notation, perhaps theta 0. This would be the external input, but without loss of generality, we consider 0 to be the orientation of the input. So this would be the input to the neuron, and we were considering the standard equation, tau Ri dot is equal to minus Ri plus G of Hi. Sorry, this would be Hi0. This was I can't remember what was the notation of the external input?
H0 of theta
H0 of theta I. Thank you. And where Hi is sum over J, Jij Rj plus H of H0 of theta I. And we were considering a particular nonlinearity function, g of x is equal to threshold linear function. And again, once we understand this model, we can start asking questions. For example, what will happen if we use a different connectivity matrix, if we perturb this connectivity matrix, and we will discuss it, or different input and different nonlinearity. This was a model that we were discussing. And then we said, okay, this is we take the limit of large N, and we're going to study the continuum limit of this set of differential equations. I apologize for the board. I will clean it during the break. So writing the if I write here, is it clear enough or difficult with this background? Difficult. Okay. So we wrote a set of differential equations. R dot is equal, R is a function of theta and t, is equal to minus R plus H of theta and t, with a threshold nonlinearity, where H of theta and t is equal to integral over all inputs, integral from integral over all neurons in the network of the connectivity matrix, J0 plus J1 cosine of theta minus theta prime, R of theta prime and t, this would be the activity of all other neurons, plus the constant input to all neurons, plus the modulated input. And I think that this is where we ended on Sunday. Right? Any questions about this equation? So from here, it's all technicalities. And the technicalities in this case would be to use the Fourier series in order to solve this equation. So the idea is that we can write R of theta and t as a sum of a constant input. This would be A0 plus an infinite sum, n going from 1 to infinity, of an of t cosine of n theta plus bn of t sine of n times theta. The idea is that rather than writing the function r in the I think it's called the normal base, we can write it in the base of frequencies, where these coefficients are just the Fourier coefficients. A n of t is equal to 1 over pi, an integral from minus pi to pi of r of theta and t cosine n theta, and similar for bn of t is equal to 1 over pi, integral from minus pi to pi r of theta and t sine of n theta d theta. And this is something that you did with Itamar. So why do it in the first place? Why does it make sense? And eventually it will work, otherwise I would not have used it. But why does it make sense? Yes? You see the symmetry. There is some symmetry in the problem, in this problem. The symmetry is a symmetry that corresponds to, well, to cosine or sine. So it makes sense to think about the problem in the framework in which this symmetry is present. One thing that I forgot to say here is that, this I think we already discussed last week, as a first step in solving this problem, what do we need to do when moving from here to here? What did we do? One thing that I forgot to say. We forgot the threshold nonlinearity. Sorry, that's we don't need it for this transformation, but as a first step, what we will do is to forget about the threshold nonlinearity. And why do we forget about the threshold nonlinearity? Well, if we find out that all values of h are positive, then it means if it's a fixed point, all the values of h are positive, then we don't care about the threshold nonlinearity. But more generally, it's difficult to solve it with threshold nonlinearity, so we ignore it. As a first step, we just think about it as a set of linear equations and worry about the nonlinearity later on. And always when we face something that is difficult, we ignore it. Okay. So the next step would be to plug the firing rate here. Next step would be to plug the firing rate here. So we will need to compute integrals of these terms times this term. But writing it using the Fourier series makes our lives rather easy. Why is that? Well, let's look at this term in the integral. Looking at this entire series, where will we see any contribution from this term? So we'll have this term times r, where r is composed of this sum. Which element will contribute to this sum when taking the integral? Well, a0 will contribute. What about these other terms? They will not contribute. Why? Because an integral of a cosine or sine from 0 to 2 pi, or in this case from minus pi to pi, will give us, well, 0. What about this term? Where will we see a contribution here? Let's look at this term, the second term.
On the A1 and B1 and A.
So this cosine can be written as a sum of cosine and sine with some coefficients. So the cosine term, and I will do it formally in a second, the cosine term will give us contribution that corresponds to A1, as you said, because only this cosine term will contribute. The sine term will give us B1. And all the higher order terms will vanish because they are orthogonal. So when doing this integral, we'll only have contributions from A1 and B1. A0 will go away, and all n's that are larger than 1 will not contribute anything. So more formally, cosine of theta minus theta prime is equal to cosine of theta cosine of theta prime plus sine of theta times sine of theta prime. So this integral, looking just at this integral, so 1 over 2 pi d theta prime of cosine of theta prime cosine of theta minus theta prime r of theta prime is just equal to cosine of theta over 2 prime integral of cosine of theta prime square d theta prime. So let's do it. do it step by step. This will be equal to 1 over 2 prime of d theta prime of cosine theta prime plus sine of theta prime times a1 of t cosine of theta prime plus b1 of t sine of theta prime. So all other terms in this series will not contribute. Questions? So the integral of cosine theta prime with sine of theta prime will go away. The integral of sine of theta prime with cosine of theta prime will go away. So we are left with an integral of a cosine with cosine, integral of cosine squared, which is equal to what? One over 2 pi integral of cosine squared cosine square plus sine square is equal to, without the 1 over 2 pi, it's pi. Cosine square plus sine square is equal to 1. Integral of cosine square plus sine square over from 0 to 2 pi is 1/2. So this is equal to a1 over 2 times cosine of theta plus b1 over 2 times sine of theta. The integral over j0 times r will give us a0 over 2 times j0. So taken together, the input to neuron theta has the following components. So this will give me j0 a0 over 2 and I also have this term which is theta independent. So this is a contribution of this term. Plus terms which depend on theta. So the first term would be j1 over 2 and here I'll have a1 times a1 of t times cosine of theta plus b1 of t times sine of theta plus the external input plus h10 cosine of theta. Okay, it's not so bad. So what's the next step? What should we do now? I'm sorry? Well, I guess positive and negative will depend on, well, being more accurate, at this stage, yeah, okay, so we want to know whether this will be positive or negative. If it's negative, then we have a problem. If it's positive, then we can throw away the nonlinearity. Well, we don't know whether it will be positive or negative until we compute A0 and A1. We don't know A0 and A1. So the solution would be, let's forget about this issue of being negative or positive. Let's assume that it's all positive. Let's compute A0 and A1 and B1, assuming that it's all positive, and then see whether the results are consistent. Okay? So I'll say it again. So we forget about this issue, this uncomfortable issue with the nonlinearity. We will assume that everything is linear. We solve it, and then we go back to ask the question of whether this assumption of linearity makes sense or doesn't make sense. And whether it makes sense or not, eventually it will depend on the parameters. Well, what are the parameters of the problem? The parameters are J0, J1, H00, and H10. These are the parameters of the problem. So let's assume that it's all positive for the time being. So what can we do with it? So we have this differential equation. What can we do with this differential equation? So in principle, well, also we'll do it in practice. We can write R in Fourier series. So if you write R in Fourier series, well, we need to write R dot in Fourier series. So how are we going to do it? Well, let's look at R. R is a function of all of this sum of things. The only things that depend on time are A0, A, N, and, well, all the A's and the B's. So if we want to consider R dot, this is R dot. So okay, good. So we wrote R in Fourier series. How are we going to solve it? So we can think about these as vectors, the cosines as vectors. So what we did by using the Fourier series is, in fact, something like linearizing this set of equations. Why is that? Because, well, let's look at the first term, A0 dot over 2. So the dynamics of the first term would be A0 dot over 2 is equal to minus A0 dot over 2 plus this term. And in this term, this is the only thing that contributes. Okay, let's look at A1 dot. A1 dot will be equal to minus A1 plus what? Plus J over 2 A1. What about A2 dot? A2 dot will be equal to minus A2 plus plus 0. There's nothing here with cosine of 2 theta. A3 dot will be equal to minus A3. A4 dot will be equal to minus A4, and we continue forever, and then move to B. B1 dot is equal to minus B1 plus this term. This is the only term where we have a sign. So now, in fact, the set of equations become very simple. So let's write down the equations. Well, the first equation will be equation for A0 over 2 dot. This will be equal to minus A0 over 2 plus the constant terms, which are equal to J0 A0 over 2 plus H0 0. That was easy. A1 dot is equal to minus A1 plus J1 over 2 A1. This is this term plus H1 0 from this term. What about A2 dot? Well, let's call it A k larger than 1 dot is equal to minus AK. No contributions for higher order terms. We have B1 dot. B1 dot is equal to minus B1 plus J1 over 2 B1 from this term, but we don't have this term. There's no input. So the question is, why do I give up the higher order terms, like A2 dot?
No, A1 I'm just coming out from A1
So, okay, so R, let's remove the dot here. So write R as the sum of, you can think about these as coefficients and eigenvectors. So the eigenvector here is 1, 1, 1. The eigenvector, the first eigenvector, n is equal to 1, would be cosine of theta. For n being equal to 2, it will be cosine of 2 theta, and so on. And we're decomposing R by these eigenvectors. So we're only looking at the dynamics of the coefficients. So this is a coefficient and this is eigenvector. So this would be the eigenvector. So I have here an infinite sum of sums of eigenvectors with a coefficient 0 to all other except for the cosine theta and sine theta and the ones. So you can think about, I think Itamar was talking about it, you can think about the Fourier series as a decomposition of R in a particular orthogonal base, which is the Fourier base, which turns out to be most appropriate for this particular problem, because the matrix, the connectivity matrix, is a Toplitz matrix, or circular matrix. That's the idea. Did it address your question? Okay, we have a set of equations, and we have the last one would be all bk larger than 1 dot is equal to minus bk. Now we should be very happy. Why should we be very happy? Because not only because it's Lag BaOmer today, but also because in each equation we only have the corresponding coefficients. So this is an equation for A0, A1, higher order terms, and so on. So these are independent equations. We can solve each of them independently, remembering your point, Musa, that it could be that everything is wrong because we ignore the nonlinearity. But as long as we ignore the nonlinearity, we can solve each of these equations independently and do the thing that we like. Well, these are linear, so it's even easier. We can look at the fixed point. We can talk about stability of the fixed point. So let's do the fixed points. So what are the fixed points? So what are the fixed points? Well, let's do the easy ones first. 0, stable fixed points. So at the fixed point, I'll denote the fixed point by a star. AK larger than 1 is equal to BK star larger than 1 is equal to 0. So we are done with these fixed points. Okay, let's talk about this fixed point. So what's the fixed point here? B1 star is equal to 0. Is the fixed point stable? Well, it depends. Depends on J. So we will assume for the time being that J1 is smaller than 2, and then we know that the fixed point is stable. We will consider later the case of J1 being larger than 2, but for the time being, let's assume that J1 is smaller than 2. Okay. What about this fixed point? So A1 star is equal to 2H10 over 2 minus J1. Just solving this equation. And again, is it stable, the fixed point? Well, if assume J1 is smaller than 2, then it's stable. Then we're okay. And okay, we have the last one. The last one is A0 star. And this would be equal to 2H00 over 1 minus J0. And is it stable? Well, depending on the value of J0. And we will assume that J0 is smaller than 1, and then the fixed point is stable. So with all these assumptions, we now know what will be the value of R. So what's the value of R? from this equation, it will be equal to A0 over 2. So at the fixed point, R will be equal to H00 over 1 minus J0 plus taking this term 2H10 divided by 2 minus J1. So this is a fixed point solution, times cosine of theta. Okay, so we worked hard, not too hard. Just to like to remind you the input. I don't know if it's still written here. The input to the network was H00 plus H10 cosine theta. So we have a network that receives this input. The input has two components. One is a constant component, and another is a modulated component that is modulated by theta. Some neurons receive stronger input, some neurons receive weaker input. The output of the network also has a constant input and a modulated input. Now, if we want to think about, so if I'd like to remind you what you did with Itamar a week ago. With Itamar, you talked about enhancement of input. And we can think about this network as a network that enhances the selectivity. So the selectivity of the input can be quantified as the extent to which the modulated input is large compared to the baseline, to the DC input. So selectivity of the input, let's call the selectivity with S. So the selectivity of the input is simply H10 over H00. That's a measure to the extent that the external input is modulated. The selectivity of the output of the network, the selectivity of R, is equal to this term divided by this term, to the modulated component of the activity divided by the baseline component of the activity. So the modulation of the output is simply 2H10 over 2 minus J1 divided by H0 over 1 minus J0. Writing it in a different way, the selectivity of the output is equal to 1 minus J0 over 2 minus J1 times the selectivity of the input. Because this is the selectivity of the input. Oh, twice. I thought you said y. Yeah. Whatever. Yes. Thank you. Again, I'm not forgetting your comment about this issue of nonlinearity. So if H00 is large enough, if this term is large enough, then we are okay. Then we don't care about this issue. Then we are sure that the output will be all positive, and then we will not worry about it. And then you can think about the role of J1. So what's the role of J1 here? The closer J1 is to 2, the larger is the modulation of the output. Or the larger is the amplification of the selectivity. So the role of the recurrent connections in this framework is to amplify the selectivity of the input. So think about weak selectivity, perhaps weak selectivity that is generated by this Hubel and Wiesel feed-forward structure of feed-forward connection that we discussed last week. So maybe the Hubel and Wiesel-like connectivity, the feed-forward connectivity from the LGN to the primary visual cortex, generates some form of selectivity to the input. Recurrent connections, if the value of J1, this element that talks about the selective aspect of the connectivity, if J1 is close enough to 2, the selectivity of the output will be arbitrarily large. So this is a way in which recurrent connections can enhance the input that the network receives. And arbitrarily weak selectivity in the input can become substantial in the output if the connections are constructed in such a way such that J1 is close to 1. Sorry, J1 is close to 2. Questions?
Don't you care about checking the assumptions about J1 and J0? I mean, just
What assumptions?
something about J1 and J2, their value at J0.
What do you mean by checking the assumptions?
Don't you want to know what's happening if the assumptions do not hold?
That we will do after the break. Sure. Yes. But since you asked, we will have no break today, and we will immediately address this question. Yes. I'm just kidding, but no, I will answer your question before before the break. So let's look at this set of equations. You will be miserable during the break. I know. You will have no friends. No one will have coffee with you. But nevertheless, you will know what happens when this assumption about J0 and J1 is violated. So let's look at about J0. So if J0 is large, well, larger than 1, we expect A0 to diverge. What does it mean that A0 diverges? This means that the activity of all neurons diverges. So this is a instability in the homogeneous direction. If J1 is larger than 2, this is more interesting. This corresponds to this term. Then selectivity diverges. So some neurons go to infinity, and some go to minus infinity. Now, some neurons go to infinity, and some neurons go to minus infinity. Well, some neurons become negative, and then this assumption about this assumption that neurons are all positive is violated, and then we will be forced to take into consideration the nonlinearity. But this we will do after the break. 15-minute break, so we will convene at 1:05. אפשר להפעיל מיזוג, אני אפעיל מיזוג.
ואז יהיה קל אחרי 5 דקות. זה לא מסונכרן.
בבניין החדש הכל יהיה טוב.
אבל יש...
בבניין החדש יש חימום וקירור אישי לכל כיסא. בבניין החדש הכל יהיה טוב יותר.
מתי עוברים? אף אחד לא מגלה לנו.
אני עובר עוד 6 ימים. בעזרת השם. מה?
אתה עובר אנחנו פה.
אתם עוברים בשנה הבאה, כאילו בסמסטר הבא.
זה מצחיק, שאלתי 2 שאלות ורק על אחת נכנסתי מחשבה. נכנסתי מסתכל לך מסתכל.
פעם הלכתי לסופר, הגעתי לסופר ואני כזה שיט,
לא נגלדת על מי.
חזרתי הביתה, זה קרה בגללנו.
אילנה שכחה, היא הלכה במיוחד לסופר לקנות מיד שילמה, שכחה אותו בחפות והלכה הביתה.
jouer sur ça.
Après, il remplace.
Il remplace quoi par quoi? H de t. C'est l'intégrale. Ah, en gros, il a résolu l'intégrale, quoi.
C'est ça.
Là, j'ai le...
En fait, c'est la linéarisation.
Ok, ça fait J0. Ça, c'est J0, il est... Oui, oui, ça fait J0 à 0 sur 2, là.
Et ben,
Que J1 sur 2, c'est tout le bordel qu'il a trouvé.
c'est l'U de H de...
Ah, c'est l'autre partie de l'intégrale.
C'est ça.
Non, là, ça c'est H. Non, je crois qu'il a résolu l'autre partie de l'équation, je n'avais pas fait ça là. Ça, à mon avis, c'est pas un problème. Parce qu'il a fait que l'intégrale de cos θ fois r θ, il a fait que ça fois ça. Il y a aussi J0 fois r θ à faire. À mon avis, c'est J0 fois r θ. Non? C'est J0 fois l'intégrale de r θ, moins r θ. En gros, tout. Ça vient, en gros, ça vient de tout.
Il y a eu H de base.
Ah.
Et le R, on a dit que c'était ça. Donc tu vas avoir J0 fois 0 sur 2.
Ça, c'est pas R. Ça, c'est...
Non, mais là, de toute façon, il a dit R fois 0.
Ah!
Ok.
Ok, d'accord, c'est bon. On va voir ça, c'est passé. Ok, après là, il met juste des points, ça fait un peu compliqué. Après A0 de T sur 2, ça, d'où est-ce qu'il le sort déjà? A0, il y a une formule aussi, c'est ça? Non.
Après, est-ce que lui, il a mis
De quoi? C'est vrai qu'il a pas défini A0.
Si, il a écrit.
Ça, c'est juste en fait, pardon. En gros, ce qu'il a fait,
En
c'est...
gros, il te dit, l'équation, c'est quoi? Si tu remplaces dans l'équation, ok?
Ok, l'équation.
Dans l'équation différentielle,
Ça va?
si tu veux, écris dans l'équation différentielle le R point. Tout ça,
Ouais.
qui est égal à moins ça, plus l'équation différentielle. Donc du coup, qui est égal à ça.
En gros, il dit tout ça, c'est égal à quoi? Je peux
Donc, c'est-à-dire, si tu remplaces, là, tu as ton R point, moins, là, tu as ton R.
Ouais.
Donc, tu dis R point est égal à moins R. Voilà.
Ok, donc ça serait mieux en fait, cette technique.
Non, mais après, tu fais un genre de diversification. Tu vas avoir R point comme ça, donc tu vas avoir A0 point sur 2, qui va être égal à moins A0 point. Après, tu continues. Ensuite, le A1, on va faire A1 point cosinus θ, qui va être égal à A1 cosinus θ. Et tu vois que c'est la même
Ah,
Donc en fait, tu vois que tu as fait tes équations, c'est l'équation de l'intégrale de la donc tu vois qu'il y a
point sur 0 sur 2, parce qu'il y a delta F.
ouais, mais justement, il le fait par identification en fait. C'est-à-dire, chaque terme de cosinus, comme ça, tu les... Ce qui est en fonction de cosinus, c'est vrai que c'est en fonction de cosinus. De ce côté, tu as une fonction de cosinus 1 θ, tu mets en fonction de ce qui est en cosinus 1 θ. De ce côté, tu as dit ce qui est en fonction de cosinus 2 θ, et là, tu mets en fonction de ce qui est en cosinus de θ.
Ok. Et alors, comment tu peux mettre ça là?
Et ça, c'est juste que je retrouve pas le H0 dessus.
Dessus, là.
Ouais, non, là, c'est pas le H0.
Oui, voilà, 0 à 0. C'est ça, là, qui va faire. Ah.
Là, tu vois, tu as un H0.
On avait un sur 0.
Non, le H00, on l'a. Le problème, c'est que ce J0 est tombé dessus. Ah, bah voilà, je peux le mettre. Ok, désolé. Bon, voilà, donc tu vois, tu as l'équation. Après, ensuite, si tu veux tout faire, t'as pas compris? Parce que, imaginons, d'un côté de l'équation, tu vas avoir un terme. Tu vas avoir non, je sais.
J'ai compris. En fait, tu fais la dérivée pour les deux côtés. Tu dis que c'est la dérivée de ça, c'est la dérivée de ça, plus la dérivée de ça. C'est ça, disons.
Ça, c'est un côté de l'équation.
Ouais, ça.
C'est-à-dire, ça, tu le mets à gauche de l'équation.
Quelle équation?
De l'équation différentielle. Là, tu as tous tes trucs en point. Donc, tu as ça.
Ok, les autres.
T'es d'accord que là, c'est un point. T'es d'accord que là, si tu mets tout ça à gauche, à gauche, tu mets tout ça à gauche. Ça, c'est un point.
Ça, c'est un point.
Tu mets là.
Ok.
Abbiamo chiamato titolare
Et ça, c'en est point.
abbiamo chiamato di chattata
Okay.
Donc, tu les identifies comme ça. À gauche, tu as
I'd like to start. Looks tasty. So we studied the ring model, assuming a particular set of or a range of parameters, and found that functionally the recurrent connectivity amplifies or enhances the selectivity that exists in the input. Now, the question was, what will happen in a different regime where, for example, J0 is larger than 1 or J1 is larger than 2. Now, if J0 is larger than 1, then we have this homogeneous instability, and the result of this homogeneous instability will be basically that if A0 saturates, this implies that the activity of all neurons, well, not saturates, if A0 diverges, in this model it implies that the activity of all neurons, the activities of all neurons diverge, which imply, well, in real neurons this will not happen because neurons saturate. So the expectation would be that the activities of all neurons in this network will go to saturation. This will happen if J0 is sufficiently large. A more interesting regime is a regime in which J1 exceeds 2. If J1 exceeds 2, then it's not true that all neurons will diverge. The selectivity will diverge. And if the selectivity diverges, some neurons go up, some neurons go down. Eventually, some neurons will become negative, and then all the assumptions the assumption that we can use a linear model, this assumption no longer holds. So this is an interesting regime, and what we will do next, we will consider this regime, and then we will relate it. We will relate it to some of the experimental results that I described on Sunday. Questions? So okay. So well, if looking at the fixed point equations, these fixed point equations are invariant to the value of J1 and J0. So even if J0 is larger than 2, these are still the equations. So clearly, the network has. Let's be more concrete. Let's put some numbers here. So let's assume that H0 is larger than 0, and H10 is equal to 0. Let's consider this regime. So all neurons receive exactly the same input, a positive input. There's no selectivity here, because H10 is equal to 0. So all neurons receive exactly the same input. So let's look at the solution. So these are still the dynamical equations. Let's look at the fixed points. So if H1 is equal to 0, the fixed point is A1 is equal to B1 is equal to 0, and A0 is equal to something. This is a fixed point solution. It's a homogeneous fixed point solution. All neurons have exactly the same value. However, this fixed point solution is unstable, because this equation and this equation, both of these equations are unstable. So what kind of solution can we expect here? All neurons have exactly the same input. So we expect that all neurons will have exactly the same output. We look at the structure of the equations. We see that the homogeneous solution, all neurons have exactly the same activity. This is a fixed point, but it's an unstable fixed point. So how will this network behave in this regime in which J0 is smaller than 1, but J1 is larger than 2? What kind of solution can we expect to get here? So we start. Let's think about it dynamically. So let's start with all neurons. All neurons are inactive. The initial condition of the network is all activities are equal to 0. So if all activities are equal to 0, then what's the value of all the A's and B's? 0. So in the Fourier, also when we look at the Fourier decomposition, all values are 0. But then we look at the dynamic equations, and we find that this fixed point, 0 fixed point, well, actually 0 is not a fixed point, because then all neurons will start, the activities of all neurons will increase until until H0 is equal to 2 H0 over J0. But these elements are unstable. A1 and B1 are unstable. So if it's sufficient that there's an infinitesimal amount of noise in the network, and then A1 and B1 will start growing. And what kind of solution can we expect here? So let's look at the symmetries in the problem. So all equations are symmetric. All neurons receive exactly the same input. So what kind of solution do we expect to get? If all neurons receive the same input? The same. So the activities of all neurons should be the same, right? But if activities of all neurons are the same, then A1 and B1 should be equal to. If there's no modulation, so then what are that? What kind of activities should A1 and A0 have if all neurons receive exactly the same input? If all neurons are the same? 0. But this seems inconsistent with the equations. So we have a puzzle here. If we consider the symmetries in this problem, we expect that all neurons will have exactly the same activity. If we look at the equation, we find that this solution is unstable. What's going on here?
Maybe what's the threshold? The inconsistency?
I'm sorry?
Is the inconsistency that we were looking for?
Because of the nonlinearity.
Okay.
Well, I mean, think about if we start with this homogeneous solution, then this issue of asymmetry, this issue of nonlinearity is not present in these equations. So maybe it will emerge later, but at least transiently it's not a problem. So this is the puzzle. We have a set of equations. Everything is symmetric, but so we're looking for a symmetric solution. But this symmetric solution seems unstable. Let's talk about a simpler problem. So let's consider. Let's have a small detour. And consider a simpler problem, which you know how to answer, that also have this issue of symmetry in the equations. So this is a set of equations. This is the x dot is equal to minus x to x minus x cubed. So this equation, well, it's a simple differential equation. I guess you all know how to solve, or at least find the fixed point. And it has this property that you can change x to minus x without changing anything. So it is symmetric. It's a different kind of symmetry. It's symmetric to a minus transformation. So what's the solution to this equation? Well, consider the symmetric solution. There is a symmetric solution. What's the symmetric solution here? X is being equal to 0. But this solution is unstable. So what will happen if we run this differential equation with some noise? The dynamics will converge to, what are the fixed points of this equation? One fixed point is 0. This is an unstable fixed point. And there are two more fixed points, +1 and -1. So there is symmetry here to multiplication by -1. But the solution, the symmetry of the solution is broken. It will be either +1 or -1. So we have two solutions. The symmetry is maintained in the space of solutions. We have one solution that is +1 and one solution that is -1. But the dynamics will converge to one of these solutions that have a broken symmetry in it. So the fact that there is symmetry in the equations doesn't necessarily mean that there will be symmetry in the solution. There will be symmetry in the set of possible solutions, but not in the particular solution that the network will converge to. And this is a simple example of something that is known as symmetry breaking. So x here is ±1. It's known as symmetry breaking. So this solution of x being equal to +1 or x being equal to -1 is a solution with a broken symmetry. So what we will do here, we will also look for solutions with a broken symmetry. Now, similar to the fact that the set of solutions here maintain the symmetry, the set of solutions here will also maintain the symmetry. But each solution will have a broken symmetry. So the solution that I'm going to consider has the following form. R of theta will be equal to J0 A0 over 2 plus H00 plus J1 A1 cosine of theta threshold limit. We don't need it to, actually. So I'm going to just to be consistent, I will keep the 2 here. So I'm going to assume that there is the solution that I'm considering has the following shape. It's a cosine plus a constant. So this is so this is a cosine. This is a cosine plus a constant. And the solution that I'm going to consider, so this would be minus pi, and this is pi. And the solution that I'm going to consider will look something like the following. It is 0 until a particular value, then it is a cosine, then it is 0 again. So this is a solution that I'm going to consider. Now, for the sake of argument, let's suppose that I convince you that this is a fixed point solution to this set of differential equations. This is a stable fixed point. What other solutions do we expect to have here? What other solutions do we expect that the dynamics will have? I'm sorry? So any solution that is a cosine, but that is a cosine that is shifted laterally by any arbitrary angle is also expected to be a solution. So the set of equations, assuming that h10 is equal to 0, has symmetry to translation in angle. So if this is a solution, then any solution that is equal to this solution but translated by a constant angle will also be a solution to this set of equations. So the set of solutions maintain the symmetry to angle translation, but each solution has a broken symmetry. The symmetry of each particular solution is broken. Yes. למה שנדבר? Okay. So the question is, what the hell is the relationship between this and what we are talking about? Okay, my interpretation of your question. So from this example, we understand that the fact that the symmetry in the equation doesn't mean that the solution has symmetry in it. It's possible that the set of solutions is symmetric, but each solution, the symmetry in each solution the symmetry in each solution is broken, like in this example. So this was a symmetry to minus. Now, this set of equations, given that h10 is equal to 0, is symmetric to translation to any rotation, if you like, to move in the angle in an arbitrary change of the angle. So I'm going to consider this particular solution. So the activity of neuron theta is equal to this function, which is basically this is a cosine plus a constant cosine through this nonlinearity of threshold, linear threshold nonlinearity. So this is a cosine. I added a constant, so this is a 0. And I'm going to, and this function, in fact, is equal to 0 whenever this is negative, and is equal to this function whenever it's positive. So I just drew it. So this is one solution. But if this is indeed a solution, then we expect that there will be other solutions which are identical to this one, but translated by an arbitrary angle. So there is a continuum of solutions. Now, the idea of a continuum of solutions should not be new to you. You've already encountered it when? A continuum of fixed point solutions? A line attractor. So a line attractor is an example of a continuum of fixed point solutions. So this solution, it's called a bump, this bump of activity, is also expected to be a continuum, expected to be a continuum of fixed point solutions of bumps of activity, such that, but the peak of the bump will be in different locations. So this is, if you want another example of a manifold attractor or a line attractor that we discussed when we were talking about working memory. Okay. So what we can do now, we can rewrite this solution in a different way. So the solution is a cosine function as long as a cosine function plus a constant. So the constant, I'm going to rewrite the constant as a cosine of theta c. So this would be theta c. And it's easy to see that whenever theta is between theta c and minus theta c, this term is positive here. And whenever theta exceeds theta c or minus theta c, these terms become negative. So I can write this r in this way. Yes. So now, just want to be to maintain a consistency of notations. I'm moving from the old notations to the lecture notes. That's why there are some issues with notations. Okay, so now the question is, one question that we may be interested in is identifying theta c. How are we going to do it? We have not proven that this is a fixed point, but the way to prove it would be the following. Let's go to the. There are two issues. One is proving existence of a fixed point, and one is proving its stability. We will only care about proving the existence of the fixed point. So let's look at the equations. So these are the original equations. Now the fixed point would be R is equal to threshold linear of H. Right? Now, with H, so H, so I will H is written this way. So now we can so the way that if the activity of the neuron has this form, then so what we did was to write H as a function of R. And so what we do now is we take the solution that we had previously on H and we truncate it. חותכים אותו באפס. So we get the positive part of the previous solution. Now the question is, what would be these parameters A0 and A1? We need to compute the parameters A0 and A1. We still keep them as parameters. And particularly, so we can. One thing that is of particular interest is this theta c, the value of theta c. So the solution that we envision at the moment is that we have a set of neurons that are active, and a fraction of the population is active, and the rest of the population is quiescent. Now, one thing that you may want to find out is what is the fraction of active neurons in the population. And this will be determined by this theta c. And in order to find theta c, well, what we need to do is to take this. We need to take this. We need to take this term. Let's do it here. So in principle, we can one simple way of doing it, we can compute A0 and A1. Actually, we will not be able to come up with an explicit term for A0 and A1. The solution would be a solution to a particular function will give you A0 and A1. But if we don't care about the particular values of A0 and A1, we only care about the values of theta c, what we can do, we can use, again, the Fourier series and write A1 to be 1 over pi and integral d theta of cosine theta times a of theta. Sorry, a1 of theta. So we can integrate this term, and then it turns out we don't have much time, so I will not go over the math, but the solution is that j1 over 2 pi times theta c minus half sine 2 theta c is equal to 1. So the solution theta c that solves this equation will give you theta c. Will give you the critical value of theta such that this is a bump. And and the dependence on the modulation J1, the modulation in the modulation in the connectivity. So from a dynamical point of view, we can now summarize the behavior of our model as a function of J0 and J1. So we said that there is something interesting in J0 being equal to 1 and J1 being equal to 2. So the regime that we discussed in the first hour was this regime, where J1 is smaller than 2 and J0 is smaller than 1. And in this regime, this is a regime in which connectivity results in amplification. The regime that we discussed now is a regime of J1 that is larger than 2. And this is a regime where we have this a solution that's called a bump state. A solution with broken symmetry in which we have selectivity in the output even in the absence of selectivity in the input. So this is the regime that we discussed. And in this, we did not compute the boundary. There is a boundary between this bump state and this regime where J0 is larger than 1, a regime in which we have amplitude instability. And in the framework, in this particular model, the activities of the neurons diverge. In other models, the activities of neurons will saturate. But this is an interesting regime. Why is it an interesting regime? It's an interesting regime because of the symmetry breaking. So if H10 is equal to 0, then all these bump solution states, all these states are solutions to the dynamics. But as we discussed in the case of a line attractor, this continuum solution is something that is very sensitive and very unstable in some sense. So it is sufficient that H10 is infinitesimally small. It is sufficient that selectivity in the input will be infinitesimally small to get this solution. That is, that will be, it is sufficient that this solution will align congruently with the input. Put differently, we can have selectivity, strong selectivity in the activity of the network, even if the selectivity of the input is infinitesimally small. So it's much more than amplification. It's an infinitely strong, if you like, amplification. The selectivity in the input can be infinitesimally small, and we'll get a bump of activity whose peak is congruent with the selective input. This is all, of course, in the absence of any noise. So this is from a computational point of view, this is a very useful and a very strong result. I'd like to go back to the experimental result that I described on Sunday. You remember I told you that the activity in the